We're going to be talking about the intermediate value theorem, sometimes abbreviated as the IVT. So this theorem states if f is continuous on the closed interval a to b and k is any number that's between f of a and f of b, then there is at least one number c in the interval a to b such that f of c equals k. So my guess is that reading that probably doesn't help you understand what this is talking about. So let's try and figure out what it's saying. So we're looking at this first graph right here. So I think we can all agree that on the interval a to b, this function is continuous just by looking at it. And we also know that when x equals a, there is a corresponding y value, f of a, right here. And there's a corresponding value for b, f of b. So the height of this function starts at a and goes up. It starts at f of a and then goes up to f of b. And k is a number that's between f of a and f of b. So k is right here on the y-axis. So this theorem tells us that if this is all true, so it's continuous, goes from f of a to f of b in height, then that means if k is in between f of a and f of b, there has to be some x value on this interval such that f of c equals k. So in other terms, this basically means if this function goes from here to here, if it goes from f of a to f of b on this interval, then it's got to go through k to get there. And there has to be an x value that allows that to happen. So we underlined here at least one number. So this case right here, this only happens at one number that it goes through this point. So if we look at this example over here, once again, we're going from a to b, and we can all agree that this is continuous. F of a is up here this time, and f of b is down here. This function has a few turns in it, though, to get there. So if k, let's put k right here. There are actually three different c values where the function has a height of k. So that's why we have to say at least one, because it can happen multiple times. So this is called the intermediate value theorem. Intermediate means in the middle. So that's the name comes from the fact that in order to get from here to here, you have to go through all the numbers in between to get there. So let's look at an example now. All right, so this first one, explain why f of x has a 0 on the given interval. So f of x is right here. So this is x squared minus 6x plus 8. And we're looking from 0 to 3. So now from algebra 2, you know that you can find the 0. But using this theorem, we're just going to explain why we know that it has a 0 on that interval. So the 0 is the k value in this case. So we need to find f of a and f of b. So we need to find f of 0 and f of 3. So first of all, f of 0 is 8 and f of 3 is -1. So the idea here is that in order to get from 8 to -1, do we have to go through 0? And the answer to that is yes, because we start with a positive and we end with a negative. So we definitely have to go through 0 to get there. Now, if I asked you this question and you got two positive numbers, then you wouldn't know that there's a 0. So you can't prove that using this theorem. Same thing if you got two negative numbers, you can't prove it using this theorem. So the idea here is that in order to go through 0, you have to go from positive to negative or from negative to positive. So our final answer here, since f of x is continuous, polynomial, so it's continuous, on the closed interval from 0 to 3, and since f of a, -1, oh, I actually mixed that up. I should have done this the other way around. I should have done 8 first and -1 second, but it really says the same thing. So we'll just kind of switch it. So f of b is less than or equal to 0 is less than or equal to 8. Then there exists a c on the interval from 0 to 3, where f of c equals 0 by the intermediate value theorem. So this is just saying, kind of in math language, what we just said, that in order to get from 8 to -1, we need to go through 0. So that means this function has to have a 0 on that interval. All right, moving on to another kind of example. All right, so verify that the IVT applied to the indicated interval and find the value of C guaranteed by the theorem. We're not using a calculator on this. Okay, so first we're going to verify that the intermediate value theorem applies on this interval. So in order to do that, we need to show that, well, our K value is 11 here, so we need to show that f of A and f of B, actually scratch that. Let me reword that. So first we need to find f of A and f of B. So A is 0, B is 5. So plug those into our functions and we get -1 and 29. So first of all, the function is continuous. You can't use this theorem if it's not continuous. Again, this is a polynomial. You need to write that. This is a polynomial, so it's got to be continuous on that interval. And we know that 11 is between -1 and 29, which is f of A and f of B. So that means there has to exist an x value C between 0 and 5, where f of C is 11 by this theorem. So again, we just have to plug in the n values of the interval into our function. And we want to see if 11 falls within that interval, and it does because we go from -1 to 29. So in order to get from here to here, you need to go through 11. So that means there does exist an x value such that f of C equals 11. All right, so then it says in this one, we actually have to find the value of C that's guaranteed by the theorem. So in order to do that, if f of C equals 11, and this is f of x, we can just set those equal to each other. So 11 equals x squared plus x minus 1. Set it all equal to 0. This is just solving a quadratic. Fortunately, this is factorable. So we have x plus 4, x minus 3. So x equals -4, x equals 3. Now this is where we have to be careful because we did get two values of x here, but we have to keep in mind that we're looking at a specific interval, 0 to 5. And -4 does not fall in that interval. So our only value of C here is going to be 3. So just be careful with when we're working with specific intervals, make sure we're staying within that interval. Okay, why do we care about the intermediate value theorem? There should be a little W here, so let's see if we can get that. We know that a function is continuous. Oh, actually, this should say if we know. So if we know, that's hideous. Let's erase that. If we know that a function is continuous and this function has a positive value of x and a negative value of x, then we can conclude that somewhere f of x equals 0. Now that's just general using 0 as an example, but it does work for other numbers too, such as in this last example we had 11. But that's what this theorem is good for.